Hello, it's Stat 135, Lecture 12. Last time we started talking about sufficiency. Remember that T is sufficient statistic for theta if the conditional distribution of x1 to xn conditioned on T doesn't depend on theta. So for example, if x1 and x2 are IID Bernoulli theta, notice that the conditional distribution for x1 and x2 conditioned on T here does not depend on theta. So is every statistic sufficient? So for example, no. For example, if you look at just the statistic that's x1, then we see that if x1 is 0 and x2 is 0, so then s is 0, so then the conditional density the numerator would be 1 minus theta, but in the denominator, to have x1 to be 0 or to have s is 0, x2 could be anything. So we have two possibilities. We could have 1 minus theta, or 1 minus theta is two possibilities. So now theta will not cancel out of this conditional density, so S is not sufficient. Today we're going to see the factorization theorem for sufficiency and also learn about minimal sufficient statistics. So let's introduce some notation where x to the n means x1 to xn and y to the n means y1 to yn. So the factorization says that T is sufficient if and only if the density can be factored into two functions, one involving T and theta and the other one just involving x1 to xn. So as a result of this, if you're trying to find an MLE estimator, you're maximizing your density. You're maximizing your density, right? So you're maximizing it with respect to theta, and so hence you'd be max. So if your density factors like this for a sufficient statistic, then you're maximizing G. H plays no role in finding a theta that maximizes your density because H does not involve theta. So what we can see from this is that the MLE estimator, so our MLE estimator is going to be some function of T. It's dependent on T. So for example, if x1 to xn are IID Bernoulli, then we can factorize as shown here, and we see that T is a sum of xi is a statistic. But of course x1 to xn is also a statistic, but clearly sum of the xi is a much better statistic. It has a much smaller data footprint. So we say that we say that the sum of the xi leads to a big data reduction. In other words, once you get your data and you form T, for the purpose of finding an MLE, we don't need all of our data. We just need the sum of xi. So here's another example where x1 to xn are IID normal. So we can rewrite this density using some trick that you should take a look at here. We can rewrite it this way, and we see that the left piece here is our function of T and mu. Here sigma squared is a constant like 5, and then the h of x is the part on the right. So by the factorization theorem, x bar is a sufficient statistic. Note that you can't factor it like this because here the g part involves not just x bar but also xi minus x bar. So in fact you could say that it involves not only x bar but s squared. So x bar s squared would be a sufficient statistic, although not a minimal sufficient statistic. So t being x bar would be a minimal sufficient statistic, in fact. But we'll see what that means later. So here I've written the density. Let's say that sigma squared isn't a constant. So here I've written the density so that our g now is a function of x bar s squared and our two parameters mu and sigma squared, and so we can see that x bar s squared is a sufficient statistic. So what we can see from this last example is that with x1 xn normal mu sigma squared, that t x bar minus s squared is in fact right. So that is a statistic, and the MLE is a multiple of that sufficient statistic. So let's talk about minimal sufficient statistics. So here, partitioning is going to be a very important idea. We're going to partition our outcome space. So first we're going to define a likelihood partition. So this is a partition given by a partition of your outcome space given by the likelihood so we say that two outcomes x1 xn and y1 to yn are equivalent if the likelihoods for xn and yn are multiples of one another, where that multiple c does not depend on theta, but it may depend on x1 to xn. So we say that a theorem that's not that hard to see is that a statistic is sufficient for theta if and only if equivalence of t implies equivalence of our data. So a way to say that is that a sufficient statistic is finer partition than the likelihood partition, in that if we have equivalence of our outcome by t, then we necessarily have equivalence of our likelihood partition. And to prove this theorem, it actually follows quite straightforwardly from the factorization theorem. Now, to define a minimal sufficient statistic, we have, so sufficiency says that we have this one-way implication, but when that implication is actually an equivalence, we have an if and only if, then we have minimal sufficient. So basically what it's saying is minimal sufficient statistic partitions your outcome space exactly the same way as the likelihood partition. So let's see an example of this. So x1, x2 IID Bernoulli. So we have four outcomes here. Now the likelihood partition here partitions into three equivalence classes. We have 1 minus theta squared, 1 minus theta theta, and theta squared. So this is going to be our coarsest partition. So you can right away spot a minimal sufficient statistic would partition the outcome space in exactly the same way. So you can see, for example, that the sum of x1 and x2 is a minimal sufficient statistic. However, for example, T0, which is basically our outcome space where every outcome is its own island or its own partition class. This is a sufficient statistic, but it's not minimal. You can tell that it's sufficient because it's a finer partition than this likelihood partition. So what I mean by finer is that you can get it from the likelihood partition by just adding a horizontal line to our likelihood partition by adding, so for example, a horizontal line between 0, 1 and 1, 0 in the likelihood partition case. So, however, T1 is not a sufficient statistic, right? You can see that just by looking at what happens to 1, 0 and 1, 1. So these are equivalent under T1, but not equivalent under the likelihood partition. And so it violates that theorem that if it's sufficient means that equivalence under T implies equivalence under the likelihood partition. So now we did two examples, I suppose, in class here. I asked you guys to work this out. So here, of course, T0, your outcome space is always going to be a sufficient statistic, but T1 is not sufficient. You can just see that by looking at 1, 0, 1 and 1, 1, 1, what I circled in purple here, that these are equivalent under T1, but not equivalent under the likelihood partition. Similar for T4, and so that's T4 is not sufficient, and furthermore T2 and T3 are also not sufficient for again the same reason. They're T2 101 is and 111 are equivalent under T2, for example, but not equivalent under the likelihood partition. In the bottom example here, you can see an example of a minimal sufficient statistic. T3 is minimal sufficient. T4 is sufficient because it is a finer partition than the likelihood partition. So finally, how do you find a minimal sufficient statistic? So the idea here is that if T is minimal sufficient statistic, what does that mean? We said that means that that equivalence under T is the same as equivalence under our likelihood partition, and so T is MSS says that equivalence under T, if and only if you have equivalence under F, and equivalence under our likelihood partition means that the ratio of the two likelihoods doesn't depend on theta. So this actually is a useful characterization of minimal sufficiency for identifying a minimal sufficient statistic. So take a look at this example here. So x1, x2 are Bernoulli theta. So we look at the ratio of the two likelihoods, and I can simplify this ratio as in the highlighted formula here. The only way that this cannot depend on theta is for the sum of the yi minus the sum of the xi to be 0. In other words, the sum of the yi is equal to the sum of the xi. So I'm going to define my sufficient statistic T to be the sum of xi. Okay, so I hope you got that, and we will review on Friday. See you then.